Project Jatayu, the autonomous unmanned aerial system team of RV College of Engineering, India, presents the Eclipse, the UAS developed for the SUAS 2019 competition. The Eclipse was designed and developed by students from various departments, including electrical, electronics, computer science, mechanical, and aerospace engineering. Significant improvements were made from last year's UAS in all subsystems. The team is composed primarily of three subsystems: the aircraft, autopilot, and imaging.
I'm Shritish. I'm a third year student from Computer Science Department. This is my second year in the team. I'm the team lead and computer vision subsystem lead. I've extensively worked on image transmission and image recognition. My flight line responsibilities include object recognition and ODLC.
I am Manas. I am a second year undergraduate student from Electronics and Communication Department. This is my second year in Project Jatayu. I have extensively worked in autonomy. I am the electrical subsystem lead and the finance lead. My role in the flight line will be mission director and primary GCS operator.
I'm Hardik. I'm a second year undergraduate student from the Department of Electronics and Communications Engineering. I'm the pilot for Project Jatayu. I have extensively worked on prototyping and power management along with autonomy of the UAS. I am the electrical system co-lead and the safety pilot on the flight line.
I'm Akash. I'm a second year undergraduate student majoring in electronics and communication. This is my second year in the team. My area of expertise is autonomy and I am the obstacle avoidance developer. I am the obstacle avoidance operator at the ground station.
I'm Abhijit. I'm a second year undergraduate student in electronics and communication engineering. This is my first year in Jatayu. I have worked on antenna design and layout planning. I am an electronic system engineer. My flight line responsibility is spotter.
I'm Nitin. I'm a second year undergraduate student of aerospace engineering. This is my second year on the team. I'm the aircraft structural engineer of Project Jatayu. I have worked on camera stabilization and payload management. I will be the pre-flight testing operator at the flight line.
I'm Manish M. I'm a second year undergraduate student pursuing aerospace engineering. This is my second year on the team. I'm the aircraft design engineer of Project Jatayu. I've worked extensively on aircraft stress management and propulsion system design. My role on the flight line will be as a safety inspector.
I'm Chanakya. I'm a second year undergraduate student. I'm from Computer Science and Engineering Department. I worked for 2 years in the team Project Jatayu. I have extensively worked on OpenCV. My flight line responsibility is camera and image analysis.
I am Naina. I'm a second year student from the Department of Computer Science and this is my second year in Project Jatayu. I have worked extensively in image processing and interoperability management. I am a computer vision engineer and my flight line responsibility will be management of interoperability.
System overview, mechanical. We have chosen the Tarot T960 hexacopter frame, which has a span of 1000 millimeters. The frame is completely modular with detachable arms and landing gear, which makes the frame easy to repair, portable, and allowing us to transport it at ease. It is made of carbon fiber. The frame was extensively tested to check its performance for an upward force of 25 Newton per arm. The electrical system overview. For the configuration of motors and propellers chosen, the current drawn by each motor at maximum throttle is 27.07 amperes. To achieve an optimal flight time of 20 minutes, two 6L 12,000 mAh batteries are connected in parallel. Other peripherals include the Raspberry Pi, autopilot, Rocket M5 and camera, which are powered using the same source through a highly efficient and a neat power distribution circuitry. Our autopilot uses Pixoc 2.4.7 along with U-Block 7M GPS module. The software system overview. The complete image processing is split into two phases. In the first phase, the image captured by the camera are stored locally in the Raspberry Pi, where it is partially processed and images having targets are selected. These cropped images are then sent to the ground station. In phase 2, the ground station performs the complete object localization, detection and classification tasks. The ground station runs on Mission Planner, which is used to track the real-time flight data and also send commands to the Eclipse. The imaging system of Eclipse uses Sony DSC HX90V camera. It has a very high resolution of 5M and provides varying shutter speeds ranging from 1/10 to 1/2000. Extensive API support is provided in order to handle all actions of the cameras hands-free. Planned tasks. For the SUAS 2019, we have planned to attempt 3 tasks: autonomous waypoint navigation, object detection, localization and classification, and static obstacle avoidance. We have decided not to perform the airdrop due to certain size constraints. Also, we will not be performing off-axis object detection due to the same reason. Expected confidence scores for mission objectives. After several tests of independent and integrated components, the Eclipse is expected to perform autonomous flights in static obstacle avoidance with high confidence while performing ODLC with medium confidence. Under autonomous flight mission, waypoint capture, waypoint accuracy and autonomous flight are all expected to perform with high confidence scores. Coming to the ODLC mission, we expect search area to be covered with medium confidence. For the covered search area, manual identification of characteristics along with geolocation and actionable format are expected to perform with high confidence score, while we expect autonomy to perform at a medium confidence score. Different types of developmental testing were performed on the Eclipse. Mechanical. With the use of ANSYS software, simulations were done on each arm of the UAS under maximum throttle conditions. Stress analysis was done at each joints and the landing gears in order to ascertain their strength and durability. After each flight mission, all screws and joints were manually checked for any possible wear. Screws were also checked for loosening before and after every flight to ensure safety for further flights. Software. We use Mission Planner as the ground control system software due to its open source license and wide community support. Using Mission Planner, flight paths, waypoints, system data including battery monitoring, distance to ground control system, altitude, obstacles avoided are all monitored. The data has been matched manually to their physical parameters. This has led us to the conclusion regarding the confidence and accuracy of autonomous tasks, which is very high. For the ODLC tasks, the output of the algorithm is tested with the real characteristics and the code has been modified in order to achieve maximum accuracy. Different shutter speeds were tested under varying airspeeds. A shutter speed of either 1/200 or 1/1000 is used depending on the velocity. Additionally, a robust GUI has been developed to allow for manual ODLC tasks. The interoperability of the entire system has been tested extensively in order to account for all possible data to be sent in their respective formats. The electronic subsystem developmental testing. A robust connection system was designed to provide power to all ESCs, flight controller, telemetry, imaging and transmission system. The connections were tested for complete connectivity to avoid high resistance paths, which cause excessive emission of heat. Before each mission, all connections are checked for loose contacts and possible shorting. During several developmental missions, telemetry frequencies of 433 MHz were used, but was later changed to 900 MHz because of their better range. For every periphery on the UAS, such as the Raspberry Pi, Rocket M5 and RFD, different powering circuitry were tested. The best configuration was obtained, which is currently used. The main battery powers all three components. Propulsion system. Different configurations of propellers and motors were tested. The initial prototype used 650 kV motors, which is later replaced by 18-inch propellers and 340 kV motors. The flight time, stability, and thrust-to-weight ratio increased in the new build. Autonomous flight developmental testing. Since autonomous flight missions were regarded with higher priority by the team, a large percentage of tests were dedicated to it. A total of 7 hours was flown, out of which 40% of the mission performed during testing were autonomous flights. In 10% of those, during initial testing, manual takeoff and landing was done. Once all basic parameters were satisfied, takeoff and landing were made autonomous too. Waypoints accuracy. For testing of waypoint accuracy, a total of 8 mission flights were flown, 4 of them without the camera and 4 with the camera, all with variable speeds. For the first 4 missions without the camera and variable speeds for 3, 4, 5 and 7 meters per second, a mean of 4.971 feet was obtained as a waypoint error and a standard deviation of 0.5584 feet was obtained. After locking on to 5 meters per second and fixing the camera, the mean came down to 4.575 feet and the standard deviation was 0.046 feet. Obstacle avoidance performance. The obstacle avoidance algorithm is further improved where the Eclipse is made to follow a much shorter path where the new waypoints get appended from the points of intersection instead of completing the whole semicircle around the obstacle. Keeping in mind the error which might occur with the GPS, the algorithm incorporates an extra safety distance of 10 feet. Imaging performance. At a speed of 5 meters per second, the shutter speed is set to 1/1500, with which the Eclipse covers an area of 165 over 130 feet per image at an altitude of 125 feet. The camera is set to click an image every 5 seconds to make sure all the area is covered while giving the onboard processor enough time to process the previous image. Object detection and classification performance testing. Based on the image data obtained from previous years and websites such as Kaggle, extensive testing was performed on ODLC tasks, which produces near human accuracy. In case a target is detected in the image is cropped such that at least 50% of the image consists of the object. Across 4 flights, a total of 47 images were tested, and each time there were 42 images with targets and 5 without targets. Among the 42 images, targets were detected and localized in 39 of those on average. Images without targets were ignored, which ensures elimination of false positives. Color detection provides an accuracy of 80%, and alphanumeric classification provides an accuracy of 70%. Similarly, shape accuracy is roughly around 75%. Localization performance. The GPS of the target that is obtained after detection is calculated by the GPS algorithm. The GPS is obtained from the PIXHawk through the RFD cable. The real GPS of the targets are obtained using a mobile device. The algorithm converts pixel distance to longitude and latitude distance. The GPS performs with an error of roughly 20 feet. Range test mission testing. To test the range of telemetry, image transmission link, and to test the maximum flight time, one mission was dedicated for the range test. The Eclipse was flown to a distance of 3 km away from the GCS. A stable imaging and telemetry connection was established with minimal attenuation of data. Flight time testing. Initially, a mission was attempted with completely charged batteries, and the Eclipse provided a flight time of 18 minutes, which provided sufficient for the team to satisfy the mission objectives. Further, we decided to test the extremes of the battery. For this, we used a pair of partially discharged batteries having a voltage of around 22 volts and landed it from a height of 150 feet. This allowed us to have an idea to set fail-safes and avoid any failures due to low battery voltage. Estimated scores from mission tests. The rubrics provided by the SUAS rulebook was used to assess the performance of the Eclipse during the competition. A total of 8 missions were conducted. For the timeline task, the team aims to score very high points, securing up to 94% of the points on it on average. The table describes the flights. The total time is expected to be nearly 28 minutes 18 seconds, which is well within the constraints of the rules. This time is broken down into the setup time, mission time, post-processing time. The mission time is expected to be 18 minutes and the setup time is slightly on upwards of 7 minutes. The post-processing time is nearly 3 minutes, which adds up to 28.18 minutes. This, applying the rules, comes down to 94.9% of the points. Coming to the obstacle avoidance task, Project Jatayu aims to secure complete points. As described by the table, different number of obstacles were tested during each flight, and barring 3 flights, all obstacles were avoided in these missions. We therefore expect to get 100% of the points. Coming to the autonomous flight, since autonomous flight was regarded with highest priority due to extensive testing, the Eclipse is expected to secure maximum points. All waypoints were captured in each of the 8 flights with very high accuracy. Once a speed of 5 meters per second was locked on, a stable error of 1.40 was obtained. On applying the rubrics, we expect to score roughly 98% of the points in autonomous flight. For the ODLC tasks, as mentioned before, 4 flights were conducted in total. Due to flight time constraints, the entire search area will not be covered. During each flight test, a total of 20 objects were tested on at mission conditions. In order to test only the ODLC task, 47 objects were additionally placed in close proximity to each other, the results of which were discussed under the ODLC performance. For mission conditions, 20 targets were used. The Eclipse is expected to cover nearly 60% of the search area, detecting 11 targets out of the possible 20. Using manual GUI tool, all characteristics are provided with full accuracy, while autonomous provides only 50%. The mean geolocation error is expected to be 20 feet. In total, the Eclipse is expected to score roughly around 48% of the points in ODLC tasks. Project Jatayu has high confidence that the team can operate professionally and with high safety during the competition, securing at least 80% of the points in operational excellence. In conclusion, accounting for the distribution of points for each of the tasks, Project Jatayu aims to score 67% of the total points. Therefore, Project Jatayu is highly confident about its readiness for the competition.